Hi. In the previous set of mini lectures, we looked at the law of exponential change, and we saw how that applies to various different systems. What we're going to look at in this set of mini lectures is, well, we'll start out by looking at the limitations of the law of exponential change, and we look at another way of describing how populations change using what's known as the logistic equation, logistic growth. We begin, though, just with a quick recap about exponential growth and decay, exponential change. Our starting point was the statement that the rate of growth of a population is proportional to the size of that population, and that's grounded in everyday observations. We found that we could translate that into this mathematical equation, a differential equation, telling us that the rate of change dp dt is equal to some constant times the size of the population p. This is an example of a differential equation, an equation that involves not just a function y, but also its derivative, dy dx. Very important class of functions in mathematics, essentially because of the myriad applications that those kind of equations have. I've mentioned this already briefly, but these kind of equations are used in modeling populations, as we've seen, in epidemiology, modeling the spread of diseases, predicting how an epidemic is going to move through a population. They're used in weather forecasting, they're used in chemistry, they're used in biology and physics, they're used in finance, and they're also used to model the diffusion of ideas, for example, rumors throughout human populations. Indeed, any system with moving parts can probably be modeled and predicted using differential equations. So given their importance, I'm going to say a few words about differential equations. One, let's first of all, just to be very clear about what's meant by a differential equation. So it's an equation that involves, well, we have an independent variable x, we have a dependent variable y, so that y is going to be some function of x. And then we have an equation that relates the first derivative, dy dx, of that function to the independent variable x and the dependent variable y. So the idea here is that g on the right-hand side is going to be some combination of x's and y's. Okay, so for example, it could be x plus y. It could be x squared times sine of y. It could be e to the x plus y. Any combination of x's and y's might arise there on the right-hand side. It's called a first order differential equation because we have the first derivative, dy dx. A solution of a differential equation. Now, up till now, I think essentially any time that we've solved an equation, it was to produce a number. For differential equations, there's a complete change. To solve a differential equation, what we do is find a function, f of x. So we want to find what is the y equals f of x that will satisfy the differential equation. So what does that mean? Well, it means we've defined a y equals f of x so that when we calculate the corresponding dy dx, equal to f prime of x, of course, that's equal to the right-hand side of the differential equation with y substituted for f of x. So basically, we'll have a solution if when we substitute into the equation for both y and dy dx, we find that the equation is satisfied for all x in the domain of the function. Just look quickly at one example. So here's a differential equation. Dy dx is equal to the square root of 1 minus y squared. So in this example here, we have g of x, y is 1 minus y squared. So in this example, in fact, this function g, which depends in general on x and y, actually depends only on y. We have our variable x limited to the closed interval shown from minus pi over 2 to pi over 2. So what I'm going to do now is just go through the calculation that shows that y equals sine x is a solution of this differential equation here. Well, how do I do that? Well, if I set y equals sine x, then I have two things to calculate. I have dy dx to calculate, and I have this other object, the square root of 1 minus y squared, the right-hand side of the equation. I have to calculate both those things. So with y equal to sine x, well, first of all, dy dx is equal to cosine of x. Okay, that's straight rules of differentiation. But also, so there's that bit checked. Now this one, the square root of 1 minus y squared, well, the square root of 1 minus y squared, y is equal to sine of x. So I'll have the square root of 1 minus sine squared x. And let's remember that sine squared x plus cos squared x is always equal to 1 for all values of x. So 1 minus sine squared is actually going to be equal to cos squared of x. So cos squared of x is equal to 1 minus. sine squared x from that trigonometric identity. So that will be the square root of cos squared x. And now, well, that could be plus cos x or minus cos x. But in this range, as the angle x ranges from minus pi over 2 to plus pi over 2 in radians, of course, always in radians when we're doing calculus, then the square root of cos squared x is the positive number cos of x. So what do I notice here? I notice that dy dx is equal to cos of x, and the square root of 1 minus y squared is also equal to cos of x. In other words, these two guys are equal to one another. Dy dx is equal to the square root of 1 minus y squared. And that's what it means for a function to be a solution of the differential equation. So when we look for solutions of differential equations, we're looking for functions that satisfy the equation. Okay, so let's return to our population modeling. As I mentioned in the preamble, we're going to look at the limitations of the exponential growth model. And we can see that if we study the population of Ireland in the 19th century. So the population of Ireland in 1821, I think this may have been the first census that was carried out in Ireland. It could have been 1811, certainly one of the first ones. Population of 6.80 million in 1821. 10 years later, an increase of over 900,000 to 7.77 million in 1831. Now, these are the kind of numbers that we saw in examples about the law of exponential growth. So if we assume that the population of Ireland in the 19th century is following the law of exponential growth, okay, we'd have y naught e to the k times t, and we could use these numbers to figure out y naught and figure out the value of k. Well, if we were to run through that calculation, we'd find that this corresponds to an increase in the population of 14% every decade. So a further 14% in up to 1841, another 14% to 1851. And if you know your history, you know that something's gone wrong there already. If we extend our use of this exponential growth model over the course of 100 years, up until 2021, over 200 years, sorry, this yields a population of 26 million. And our population, of course, is nowhere near 26 million. So this exponential growth model has this problem. It works very well over the short term, but it does not work well over the long term, because what we find is an exponential function that just gets bigger and bigger and bigger and bigger. And of course, we've entirely missed here the effects of the famine and the mass emigration that occurred after that. Okay, so this exponential growth model is always going to go wrong if we try and extend its use over long periods of time. So that's the moral of this example here, is that the exponential growth population model breaks down if we use it over extended periods of time, even without the catastrophic effects on the Irish population of the famine and the mass emigration that followed that. Even without that, we would find that the population model is inaccurate. It doesn't work well in any country when it's extended over long periods of time. We need a better mathematical model. And that's what we're going to look at now, the logistic growth model. So the logistic growth model says, yes, okay, population change is mostly governed by the size of a population. Again, referring back to the difference between Ireland and India, the big population of India means that there's more people born every year. The much smaller population of Ireland means that there's far fewer people born every year. So that starting point, we'll still hold on to that. So in our mathematical model, we're going to include that term there that we have from exponential growth. So we're going to try and make some statements about what other features might be included in a rate of population change. So our first thing is a positive term that's proportional to the size of the population with a positive constant of proportionality. So this is exactly the part that we see in the exponential growth model. What we're going to look at here is what else we might include to make this population growth model more realistic. Well, what could influence a growing population? What could slow it down? Well, as the population grows and grows and grows and grows, following that exponential growth model, just getting bigger and bigger, growing exponentially, multiplying by or increasing by 14% every decade, well, the place starts to get full. Resources become scarce, and there's competition for resources. So the next input into the logistic growth model is a term that basically represents competition for resources, which, as we'd say, acts on as a brake on the population. And this is what we see in real world populations. Okay, so the second term that we include in the rate is a term that's proportional to the square of the population, so p squared, and that has a negative constant of proportionality. So the positive constant here, this causes growth, but the negative constant there, that's going to be a decaying term, or if you like, maybe better to say that that acts as a brake on the population, slows it down. Why the square? Two reasons. First of all, it's simple. It's a very simple term. We understand how it behaves mathematically very well. But also, the square of the population size P. Well, let's imagine P equals 10. Let's say we have 10 people in a population. And let's imagine that they're fighting over resources or competing for resources. The amount of competition we can think of as depending on the number of interactions that we could have. And 10 people, well, we can match them up in pairs, essentially 100 different ways. Okay, we've double counted there, so we need to be careful. But basically, the square of the size of the population is counting roughly how many competitive interactions there may be between individuals. Okay, so literally fighting over food or competing in an economic sense for resources. So for every one of those 10 people, there's another roughly 10 people. It's going to be 9, of course, but there's roughly another 10 people that they might be in competition with. So this p squared represents that. It's this simple way of representing the number of competitive interactions that might take place in the population. Okay, so that gives us this logistic model of population growth. And let's see how that translates. Well, there's our part from item 1, the original exponential growth term. And here's our additional term from competition, minus L times P squared. So this is our logistic differential equation. And we're going to spend some time analyzing this and looking at applications of it. Okay, before jumping in though, I'm going to change this slightly and say, okay, well, I have a factor of P in both of these terms. This is P times K minus L times P. And in fact, I'm going to take out the K as well. It turns out to be very convenient to take out the K as well. So that would be 1 minus L over K times P. And then as a very last step, kind of, and why do I do this? Well, I do it because I know it's going to be convenient later on. That L over K, I'm going to call that 1 over N. Okay, so what I'm using there is I'm going to introduce a new number, N, which has the property that 1 over N is equal to L over K. Or if you prefer, that's just N is K divided by L. Okay, so that's just a slight rearrangement done for convenience, and it produces this logistic differential equation. And what we're going to do next is analyze the consequences of this differential equation. So see what kind of populations does this describe. Remember, our original exponential model gave exponential growth. So with this logistic term in it, there's some kind of brake on the population. And what we'd like to do is figure out what way it's going to evolve. Just some terms, as before we call K the growth rate, and this number N, it's called the carrying capacity. And we'll see why it's called that after we solve this logistic differential equation.